Yeah. So anyway, so as you can surmise, same on both screens, right? Um, this is the course resources page for the class, which also exists, I guess, under Canvas. Is that, that's not Canvas. Too many screens open. This is Canvas. And so all the material that you see here, I guess the syllabus is available on Canvas, which is here. No, it's not there. It's course resources page, syllabus here. So you probably don't need me to tell you too much how to navigate around Canvas. Perhaps introduce the general outline for the class. Course resource page. Let's go through the individual components. Just too excited by this. So on the course resources page, we got a syllabus, which we'll talk about. The course notes, which are the same horrible notes that you suffered with 303. They've evolved over time but haven't changed much. But those will be the things that I used in class together with my own handwriting. So that's if you came to class or if you ever looked at the recordings, you'd know that was the deal. A previous website has the same stuff online that's not so readily accessible. So I would suggest you download this big document. The syllabus you have in your hands, but it's also available to you. YouTube channel you don't need to go to directly because you get ported there by the course resources page. And the assignments, which are submitted Thursday midnight again. And there are a total of 8 of them. 8 doesn't exist. There's 1 through 7 plus 9. And those are available here, but also here. And they're due online. Students have been delivering them online recently. Prior tests are available. You can see that this class has been taught since 1997, if you can read that. And I just put up last year's test, which is this. It is on the Tuesday before spring break. It's in class. It's closed book, closed notes, but the questions that you probably have to choose from are probably 6 total, and the test is 3 questions. And so you can easily prepare beforehand for that. Well, that's probably better, isn't it? Prior tests, the first half of the class is essentially over in terms of most of our material by spring break, with only a few afterwards. And so the material in short form for the whole class is given on these 2 sheets of paper. So if you understand everything on those 2, you know everything you need to know about this class, I think, to get through it. Part of the class is to prepare a presentation, not unlike in 303 in groups. So if we have 15 or so in the class, I guess there'd be groups of 3-ish or 4-ish. We don't necessarily need to do all 6 topics, but the remediation part of the class is all done by yourselves in putting together a presentation and presenting it. It used to be in class live, but now it's online and with a quiz that you supply given to the other 5 groups, if there are 5 groups. And we'll talk about that in due course. And how to turn a narrated PowerPoint into a movie. You probably know how to do that. The material for that. It's quite quiet, actually, considering they're demolishing a building next door to us. I get you to fill some forms in. This, so we'll peer review. So when, I guess we're 5 years almost to the day out of COVID, right? So this class first went online for COVID, fully online, and the presentations, of course, were online as well. And so to keep people up with their activities, to try and get them to do things early, then I get you to meet as a group, probably just before spring break, and to fill out some forms of who's going to do what and try and keep you to it. And what else? The remediation tasks, and then peer review, how you evaluate each of your peers. And you've just seen something like this before, how everyone did. So you get to evaluate your colleagues, and so it's usually a little bit different from 303, because by the time I think you know all your colleagues, right? It's a cohort that's moving through together, whereas in 303 perhaps you did not know all the people around. So that's kind of the scope of the material. So everything's served to you online. This is the materials for this. I guess I don't want to see that. Is all the material is in your contract that you have in your hands. We're here now, so you know it's 308 in Hammond Building. There are a couple of resources that we have online as well. If I get this. I think these are the YouTube videos, which you don't really need to go to. This is the resource page that you get to just by searching on my name. It's the easy way to find that. There is a textbook. I don't know how many people buy it. It's by Colin Feder. Was by Colin Feder. It's now by two other co-authors. It's Contaminant Hydrogeology. Available in the bookstop if you want it. I don't know what books are now. They're $50 to $100, I would imagine. I'm not sure that a huge number of students buy it. There are also some texts, and I'm not sure if anyone uses these in the library, that have kind of grown up over time. One that's a bit dated but is useful for the remediation stuff is this EPA report, which is available online actually as well. And the other ones are, the first part of the class we use dynamics of fluids and porous media, but all these things are mashed into that PDF that you can download. And so if you want to, you should download that, and you probably don't need to go to these other resources to back it up. The instructors are me. I guess I'm the only instructor. Matt's the TA. I have an open door policy. If you want to come and chat, please do, in 231 Hosler. Matt, whose face you saw on the Rogues Gallery just now, is next door in 230A, and so he's available. Students tend to go and visit often after the class on a Thursday, before things are due on a Thursday night. And so that's when most of the activity occurs with Matt. In terms of the deliverables, we talked about the assignments 1 to 7, and 9, roughly equally weighted. I think one of the early ones is worth double. Maybe the third one in, or the second one in, is worth double the other ones. And those cumulative are worth 35% of the grade. Midterm, which is the Tuesday before spring break, is in class and is 25%. You can choose to come to class if you wish, in which case we'll gather names and I will put your score into Canvas, Canvas for the quizzes automatically. Maybe at 1.5 times the score, I'm not sure yet. And if you choose not to, then you just do the quiz, and that takes care of it. The remediation presentations are in the latter part of the class, certainly after spring break, probably starting in early April. And they're, depending on the size of the class, with 15 students, perhaps we'll do, having a group size of 3 or 4 is perhaps optimal. 3 might be a bit small. We could do 5 at 3, or we could do 4 at 4, I guess, yeah, roughly. And so we'll divvy those out based on what we've had in the recent past, and we can look at that on the course resources site, and that's worth 25% of the grade. And then you learning from your peers by viewing the recorded presentations and taking the quiz for all of them, however many of them are, is a 6% added on. So even if there's 4, it'll be 6% just because we'll do that. And so the total score is 106%. The grading scale is this, just the same as in 303. So an A is above 93.3, A minus to 90, etc. B's are 80 to 90, C's are 70 to 80, etc. What else? Yeah, so that's pretty much the way we run the class. So you're welcome to do it any way you wish. Some will choose to come, some will choose to never come, and so either's fine. You choose what's the best value-added deal is for you. It tacks on to 452, which you must still take in this major, right? Hydrogeology. Who you had it last semester? Who taught it? Yoxtimer? Byron Parazak? Yeah, okay. Yeah, nice guy. Great guy. And so it follows on from that. So GSci 452 always used to be physical hydrology, physical flow of fluids. And so we're more interested in contaminant hydrology, tracking the motion of a fluid being advected by the motion of that water, and then how it travels in the subsurface, how it is transported by the bulk motion of the water, how it's attenuated by being sorbed onto the soil it goes past, and how it is diluted by diffusion, and what methods we might use to be able to remediate that. So that's basically the content of the class. It follows the book chapters that we have. You don't need to have either of these books to be successful, I think, in the class, because I'm guessing that most students haven't had that. And the topics we deal with are physical hydrology in terms of motion of fluids in the subsurface, except we will talk about not just a single fluid traveling, but multiple fluids. So typically oil and water, as in petroleum reservoirs, or solvents and water, as in, well, because gasoline is a solvent also, in underground storage tank spills. We'll talk about the mechanism by which the phases travel separately when they're present as two separate phases, traveling as gasoline and water traveling in concert. We'll talk about when they get to a location where they don't move anymore, how diffusion occurs, and that the contaminants will diffuse at with the help of the water that they're dissolving into, how they might attach onto the solid substrates of the grains of soil in the subsurface and be diluted as a result of that sorption, and be attenuated as a result of that. Most of the components we'll talk about are volatile, and so they can vaporize at relatively low temperatures and at low pressures that we find ourselves at. And so we need to talk about how those are mobile in the vadose zone above the water table. We'll briefly talk about mathematical models to be able to solve for both flow part of the equations and for transport of the contaminants moving on top of the flowing water. And so that'll typically come, so spring break is in here somewhere, and this is before and after. So obviously, if the test is at spring break, this is the last topic, which is on that before we move to the more practical side of things. And we'll talk about methods of site investigation. You'll do lots of kind of assembled questions. The assignments are basically questions. You have a spill, it's this is the stratigraphy, these are the characteristics of the materials that it's spilt into. And this is the geometry of the in situ fluids. This is the geometry of the plume that has come from those. And so with that information, you have to make some design of how you might remediate it. But the question is, how do you know what that initial picture is before you go in there? How do you know when you're standing in a field that has no particular important characteristics that would lead you to say anything about it? How do you know what the plume looks like? How do you know what the concentrations are? How do you know how quickly it's able to travel? And so to do that, you have to do things like site investigation, how you drill and take cores, different methods for different materials, and augmenting that with different methods of geophysics as well. Now, there used to be a environmental geophysics class in geosciences. Anyone taken that with Andy Nyblade? Don't know if it still exists. I think it's this semester, if it still exists, and you'd be more likely to do it now at the same time. And then remediation. So you know that you have a problem in this field which you can't tell what's going on. There's something in the subsurface. What are you going to do about it? And how do you rely on what we've done before in terms of knowing about how fluids travel in the subsurface, how they carry contaminants with them, and how those contaminants are attenuated, or how those contaminants might not want to move from their initial position? What methods are available to be able to recover them from the subsurface? So we go through a full cycle, I guess, from messing the place up to actually remediating it up. And I think between then we'll actually have Jason McNew, who's a graduate of your program, Environmental Systems Engineering. Is anyone here not from Environmental Systems? No, didn't think so. So he's a early 2000s graduate from your program. Well, it might have been called Geoenvironmental Engineering. It's gone through a couple of one name change actually. And Jason will give an online pre-recorded talk. And that's kind of the boilerplate for don't cheat. Submit your work together, but submit your own work. This is a calendar of what's going on. I guess we won't meet this Thursday rather. Actually, I can do circles. Oh, fantastic. We won't meet that Thursday, but we'll meet most of the other ones as far as I know. This is the date of the midterm, the first Tuesday in March, the 4th. And this is a due date for the presentations. So those are the dates that you might want to remember. So that's pretty much it. And so these are just the individual topics that we've talked about. They correspond with a bit like 303, each topic, a basic synopsis on what it is on one page, and then some stuff that we'll talk about, either deriving some equations or writing some stuff down or using some boilerplate that's already there. So that's our plan. Questions? Of course.
I just want to clarify. So those quizzes that are on campus, those are either you show up in class or you do them?
Yes.
Okay. So it's not like...
If you show up in class, I'll take your names and I'll put your score in. And it'll be a full score. Might be 150 instead of 100, I'm not sure yet. I'm not sure why. I'm kind of curious to see what the pain threshold is for coming to class, you know. If you get 150 instead of not coming to class and getting 100, is that enough to come to class? If you get 500 to come to class and 100 online? If you get 101 to come to class and 100 online? I'm kind of curious. What do you think the pain threshold is?
I think it's just the timing of the class. 8 a.m. is a little rough.
This isn't 8 a.m.
No, but like
3:03.
3:03.
You don't like it?
No, wasn't
fine.
my thing.
Fine. Did you look at the, without, I don't care what the answer is, but did you look at the videos?
Yes.
Do. Oh, yeah. So I'm never quite sure whether people do. Great. So what a great guy I am. Providing all this stuff. Yeah, to me, I used to get annoyed if people didn't come to class. I'm way over that. And so it's just providing stuff that you can do it the way you want to do it. So that's fine. So it works out fine for everybody. No other questions? Well, what else do we want to talk about? Well, I can talk in more detail about some of the individual components if you like. What do we need? The assignments. So actually, if there's one thing that the students I don't think like in this class, but I think is a necessary component, are the assignments. And that's because they are kind of open-ended. Does it go through there? See, they exist here, and they're probably linked. And so they are open-ended questions where you have to make some choices on what your parameters are. There's not a single answer to 3 decimal places that comes out of it, but they're more conceptual. And so they're not so tightly constrained as Munson type questions from 303. And so it's getting you ready for your career. I think they're all real world examples that have some influence and require that you have some conceptual understanding of putting together, and it's not really fed to you on a plate. So to help you doing that and to make my life easy as well, it's not completely altruistic. I guess a little while ago, the worst form of this class I ever did was when I flipped the classroom, and the deal was that you could look at the material online before on the videos, come to class with questions of what you didn't understand, and we deal with it. And then we'd spend the rest of the class just going through the homework assignments. So invariably what happened was, maybe in this class of 25, there were 2 people who looked at the videos and were, they're the grade busters and had no questions. The other 23 students, I don't think, looked at the videos, so had no questions to come and answer in class, so that was kind of a bust. And then wanted just me to go through the assignments, which I did. But anyway, when we did that, maybe for the first few, I recorded them. And so I'm not sure whether this is the easiest way to do it. But yeah, they're scrappy, but they're online. So this is just the assignment we looked at, which is the old Yucca Mountain site. How long does it take if you break radionuclides out of an underground waste repository? How long does it take to arrive at a compliance point that's 25 kilometers away? And so this is how to do it as we did it in class. I think more useful to you and actually available for all the assignments is some guide on how to put this together. Not telling you what the numbers are that you need to use, but at least being able to rationally give you a few hints to get you moving in the right direction. So that was put together, well, you can see 2018 by Chow Yi Wong. I remember put those together for all of the things. So those are the assignments. The assignments come with each probably second class. So they are every week, 2 classes every 2 weeks, etc. They're largely done by the time we get to spring break. I guess 6 out of 8 are done by the time we get to spring break. Yeah. And I think actually, no, this assignment 7, you probably have due after spring break, some time after that. So that's that. The prior tests, if we take an example of one, it's this is the third Tuesday. This is unusual. This is last year, and for some reason, but I can't remember why, we did it after spring break, and I can't remember. Yeah, this is after. It's this year. It'll be the Tuesday. It'll be on March the 4th, Tuesday, March the 4th, and all the same format. The question 1 is a brain dump for 10 different things. These are all things that we'll talk about in class in each of the materials, and I'm just asking you to dump everything you know about hydrodynamic dispersion. What is longitudinal dispersion? What is D star? That's diffusion. What is alpha L? Well, it's the mechanical dispersion coefficient. This is advective velocity. We find out that it's scale dependent. It's roughly proportional to 1 over the length scale of the size of the plume. And so it's not really a parameter per se. And so I'm just asking for you to write down all those things. The other 2 questions are calculation questions. They repeat. There are probably only a total of 5 or 6 individual questions, of which you'll get 2 of them, and so they probably repeat every 3 years, something like that. You won't know which ones in advance, and I don't think there are solutions going around because I haven't provided solutions to them like I have done like we do in 303. All the exams have solutions attached to them. So these ones aren't circulated, hopefully. So with 6 questions you can prepare beforehand. You know it's going to be a relatively small group of questions. And there are 2 questions that ask you to do some very specific things. And you know in advance somewhat what those will look like. And so that will be before spring break. There is no final now. We don't do that. What else? Remediation tutorial. The background for this, I guess we can talk in more details. There are 6 topics, 6 different ways of being able to remediate sites, and those are the 6 that are there. Those methods are actually included in the course notes, right at the end of it. I guess I won't do that, I'll go through this. So this is geophysics. And so if you look at this, so there's some material on this. The stuff on remediation is taken from the text that I mentioned in the list on your sheet. It's by Grubb and Sitar. It's the last of the 5 on the 2nd page of your syllabus. And it talks about these 6 methods written out here. And each of them are divided between the topical areas that I would like you to address in your presentation. So they each talk about, what the topical area is, how it's implemented in the field. Actually, it's not so obvious from this. Examples of it, where it can work, where it doesn't work, how much it costs to do it, which are per cubic meter of soil treated or per volume of fluid, etc. And so those details are available there, but I'd also refer you to, on the syllabus, it follows exactly the way it's set up in this reference here. Bit dated, as you can see, but it's not a bad way of getting a grounding in this. And in the tutorial rubric, you'll see that these are the exact same 6 points that are mentioned in that EPA text. It's a report to EPA. And so what I want you to do is be able to talk about the physical mechanisms. So we'll talk about flow in porous media, how single and multiple fluids flow, how some fluids get stuck in there by capillary action and you can't get them out, and how does that relate to, for instance, remediating gasoline as a free product in the subsurface. So talk about the physical mechanisms that govern the motion of those contaminants into the subsurface and the recovery from the subsurface. Say what features influence it. Is permeability important? Is the presence of organic materials important for sorption in not allowing it to be recovered? What are the methods for doing it? Do you drill some boreholes? Do you excavate? Do you dig some trenches and circulate fluids from those trenches? Do you excavate the site and take it to a landfill? How well demonstrated is the method? Is it a theoretical method that's just in its infancy, where people are doing lab studies to be able to see whether it can work? Or is it something that's been used for 20 or 30 years? What limits its use? What if you're trying to pump fluids in the subsurface and you have contaminants that are in clay with really low permeability, there's a pretty good chance that you can't get anything out of those by pump and treat. And you have to use other methods to be able to do it. So the characteristics of the subsurface make some methods impractical and impossible, and other methods, bless you, much more feasible. Some of the most difficult data to get are the costs and its availability, but Actually, there are EPA volumes that now do that. So those are the 6 things that you're asked to comment on. And so you've probably made enough presentations in your university career to realize that the best thing to do is to meet early on, figure out who's going to do what, and bring it all to the table. And so just to keep people on track, the idea is to provide a tutorial that lasts for something like the 75 minutes that we'll be here, hour and a quarter for these Tuesday, Thursday meetings, even though it'll be done and recorded online. I'll get you to meet before the end of week 6. I guess it's 8 weeks before spring break, so it's close to spring break, to divide things up. I guess we'll wait till we get a couple of weeks into class before we divide you up into groups, in case we get a huge influx of people, or if everyone bails, then we don't end up with groups that have missing people in them. I'll probably assign a group leader, or you can choose your group leader, and then submit one form that has the breakdown of what people will do. I guess it was this form that I mentioned before? This is it. So I'll get you to submit this form here, which is pretty straightforward. You will have been given a topic, and then you'll decide for me to communicate. There's no communication needed, actually, but then talk about who's going to lead each of these things. I think it's useful for you to do. Actually, I'm not going to use this at all, but it's useful for you to know what you have to do, because rather than meet and stare at each other across the table in the library, it's better to just deal out the tasks and bring them together. And so if you're using PowerPoint, you can put them all together in a single slide deck, make them independently, agglomerate them in a single slide deck. Actually, you can do it independently, add your narration to it, then assemble those in a single slide deck, and then create a movie from those, straightforwardly. And even, I guess, on the website here, I think that's exactly what this is. You've done this before, right? You don't need me to tell you how to do this. Is that going to run? Is it running? No. Volume off. Yeah. So it tells you how to do it. You know how to do it. You've done it in 303, yes? Yeah. Do it anywhere else? Oh, such life skills. What a class. I guess I'll kill that so I don't have to listen to it. So, very easy to do. What else? Okay. Where do I need to be? I don't want to be on that page. Do I have all those things open? I want to get back to the other. I guess that was a... Fine. So is that... Oh, that's EndNote, so I want this. Oh my God. So what else? So you got the mediation tutorial. Yeah, and so the other thing, I guess, which is implicit in that, is that each of these topical areas, if I can find it again, have a score attached to them. So I'll give you some feedback. I'll give you a final score. I guess like 303, we modify that final score to account for participation, right, by 15%. 15% for the individual and 85% for the group effort. And because we put them online, you will supply 10 questions, multiple choice questions, and those will go on, just to encourage you to actually learn from your colleagues' work. Can speak more about that. I will say that and I don't know why, I've said this many times, one of these soil washing, air stripping, and soil washing methods, some talk about doing this ex situ. This is an in situ class. So if you're doing 4 or 5, do it on material that's relevant to this class. Even though I say it, people talk about, it's just the easiest stuff that's available online, and we talk about ex situ air stripping. So we dig it up, we put it in a pile, we circulate air through it, and then we replace it back. Don't do that. It's in situ methods that we're interested in this class. So what else are we dealing with? Anything else? Peer review? Yeah. What else? Anything else we need to talk about? Well, let's go very quickly through just a brief discussion of what we'll talk about in the class. Very quickly. So, I don't know. We tack on to where 452 would have left off in terms of groundwater hydrology. So almost all the water supply in State College comes from groundwater. It used to be that Bowlesburg used to get its water from next to the ski hill, Tussey Mountain, from Spring Creek. After multiple boil water alerts, maybe 30 years ago, they changed it to all groundwater. So it's all supplied by groundwater in this region. And so we take 452 as kind of the basic understanding for this class. Some of the things that are going on in this area is that if you look at the groundwater supply, all the groundwater supply in State College comes from fault zones. So these are horizontal faults and fracture zones, which are strike-slip faults like the San Andreas Fault in California. And those, because they are deformed and fractured, they act as excellent receptors to gather the surrounding groundwater into a very long fractured rock trench, which you can then put a borehole in the center of it and the fracture zone has a high permeability and so is able to gather water very effectively. And so this happens to be a fractured trace in Huntingdon. An interesting project that I was involved in, actually it's probably almost 30 years ago as well. And that is the town of Roaring Spring, which sells its own bottled water, but also has or had a paper company, the Appleton Paper Company. And they were worried by the plans for deepening of a limestone quarry, New Enterprise Stone and Lime, which at the time quarried with a couple of benches, probably, 50 feet deep or so was its current depth. And the hydrogeology of that site was that there was a fold with a steep vertical side on one side and a shallow side on the other side, kind of shown here in cross-section. And on that zone, because of the deformation that occurs on the hinge, which runs along the length of this buckled, so this is the strata, they're deformed like this. This gets stressed, and so all the way along here, you end up with this fracture zone, which is kind of epitomized by this. So this fracture zone gathers all the groundwater flowing to the west in this very permeable conduit, and it carries it down gradient as it drops in height into the Roaring Spring, which comes out as a spring in the town of Roaring Spring. But the concerns of the paper company were that the reason that this works as a viable quarry was that these vertical beds, which are really quite low permeability, act as basically a groundwater dam. So this fracture zone is super permeable. It's transporting water towards me and away from you, into the page, so to speak. And this acts as a groundwater dam, and it gathers all the groundwater that's traveling from from the east westwards. And so the worry was that if you deepen this by creating extra benches sequentially, was that you'll allow all these rocks to move and displace, to fracture, and all of a sudden the groundwater dam, which was very effective in piling up the water behind it, will allow stuff to come through, and all of a sudden the spring, which was was flowing in Roaring Spring, won't flow anymore. And so Appleton Paper took Roaring Spring to court. DEP were the arbiters of dealing with that, and their solution was to allow Roaring Spring to go down one bench at a time, to monitor this for any deformations, monitor it for any changes in water. So if you saw water gushing out of here, then all of a sudden, might be too late, but then you'd stop, and then there would be no other permit given, and then that was the worry of what's going on. I went back there actually at the end of COVID, and it's absolutely a bone dry pit, and they must be down a couple of 100 feet. It's really, really deep now. So I guess we did a reasonable job of making the predictions that it wouldn't destroy the Roaring Spring, which still produces bottled water. And I think Appleton are still in. Actually, I don't know if Appleton are still in business. Anyone live in Roaring Spring? Anyone from Pennsylvania? Yeah, most people. Yeah, I'm not going to talk about Nivelle. A surface mine in India, where I guess, yeah. So it's next to the Bay of Bengal. So if you take this as being a map of the Indian subcontinent, not Madras anymore, Chennai, I guess. Nivelle is just in Tamil Nadu, 100 kilometers south of there. It's a lignite seam, which is close to the surface, in which the water pressures underneath are high because they have a high groundwater table. And it's also next door to the coast. And so the problem here is, one, the water pressures are so high that when you take away the impermeable coal, all of a sudden you're swimming in the pit because there's so much water goes into the pit. And secondly, so you can pump that out, and it turns out that all the area around Nivelle is very verdant and lush because they use it for irrigation, and further away it's much more arid. And secondly, the other problem is if you're pumping water here, then you get the same problem as you get as a problem in Florida, and that's groundwater intrusion. So if you're sucking fresh water out of here, and the coast is over here, then the water table will go out to here. I don't know why I'm drawing with my finger when I could draw here. And what you get is a saltwater wedge. So this is salt water. And so what you get is an intrusion of brine into this. And the more that you pump out of here, the more you bring that wedge in. And so ultimately, at some stage, you can be pumping salt water in. And if you're using that salt water to irrigate fields around here, that's not a very good outcome. And so the problem was to make sure that you can limit the flows into this, and also that you limit the magnitude of the salt water incursion into this. So this is the sea here, and you'd end up with a brackish wedge which comes in where this is salt water. And so this, I guess, is a mixture between groundwater hydrology, pumping, single phase flow of just water, single phase flow of just brine, salt water, with the salt dissolved in it, so but different components of that. Radioactive waste disposal. Around the world, all the developed countries that have nuclear power, Canada, the US, UK, Germany, Sweden. I guess it's easier to talk about the countries that don't. North Korea, I guess, South Korea. Not Australia, not New Zealand, not Norway. Must be many other, not, I guess Argentina is. All of them have to deal with their spent byproducts. And so the current views of how to deal with this are to take the wastes, put the wastes in metal canisters, typically steel and with copper cladding, put the copper inside the steel, put the steel inside an underground repository where it's backfilled with something, typically bentonite clays, which are low permeability and have high sorption potential, and then isolate them geologically so that you have this kind of multiple barrier concept. So you've maybe put the radioactive waste in glass, bonded it within glass. You've put it in a copper canister, within a steel canister, within a bentonite sheath that's in a tunnel that's underground, within a rock, which is maybe 300 meters or 500 meters deep, and then you seal it back up and you go away and forget it. You expect it to be there for 100,000 years to 1,000,000 years, and so you realize that 1,000 years ago was William the Conqueror in 1066, just 1,000 years ago. And so if you're leaving it for 100,000 years, that we might not be around then, and so you put some plaques on it that are to allow people to not dig it up, etc. So, those are the time scales that you're talking about. And you want to be able to do some engineering to be able to say whether in 100,000 years, which is the EPA requirement for the calculations that the repository will act as a repository and actually contain the wastes to some level of small fugitive emissions. So do the analysis to do that, and you want to provide credibility for that analysis. So the US doesn't have a plan for a radioactive repository. The ones which are most advanced would be in, if I look on this map, these lines are all stress contours, in situ stresses within the crust. And obviously these repositories are in crustal rocks, and so they're not in soils. These are high-level radioactive wastes. And so what matters are the stresses and the propensity to have earthquakes which might breach these repositories. And so the most advanced of the nations that have these going, Finland and Sweden, are currently starting to inter radioactive wastes. Most of the other industrialized countries are not so close to it. And so the question is, what will happen over 100,000 years? How many canisters will break due to the loading in the subsurface? Will earthquakes affect them? Will the heat that's generated by the wastes breach the canisters? Will it be carried to some compliance point where people will feel it? Yucca Mountain, the previous one for the US, is 120 kilometers from Vegas. At that time, the fastest growing city in the US. And what will be the effects of them if they spill? So contaminant hydrology would be the mechanism by which breached radioactive waste from these containers get carried downstream, down gradient in the subsurface by the motion of the groundwater flow. So that's your first assignment. You'll get to do something to calculate how quickly will it arrive at this compliance point downstream, and in what concentrations we'd expect it to arrive as well. So that is one thing. The time that we'll spend focusing on most of this is perhaps the most difficult problem in contaminant hydrology, which is the motion of D-naples and L-naples in the subsurface. So naples, you probably know, is non-aqueous phase liquids. They can be lighter than water, such as gasoline, which if they're spilled, because they're lighter than water, they would float on the surface of a swimming pool, but they'd also float on the surface of the water table. And so if you look at the subsurface water and the groundwater table, if you have a spill from the surface, you'd get that going through the vadose zone, which is just the same as a porous medium with nothing else except air in it. The gasoline, maybe 500 kilograms per cubic meter, is more dense than air, but less dense than water. So it'll go through the vadose zone until it meets a barrier, and that barrier would be the water table, which originally would look like this. And the water table, where it's fully saturated with water in the pore space, above the water table in the vadose zone, it's partially saturated with water and mainly saturated with air. And so what it will do is it will depress that water table, and you'll get a lens, if you like, of non-aqueous fluid. So the gasoline will sit as a puddle, if you like, on top of the water table. This will provide a chimney, which will be a smear, if you like, of gasoline which is present, that can volatilize because it can evaporate from the subsurface. And so that's one mechanism by which it can move in the air-saturated subsurface. It can roll down the water table, actually not very easily, because it's held by interfacial forces, surface tension, which is quite strong. That's why we talk about surface tension in 303. It will slightly depress the water table because of the supernatant weight of the gasoline is larger because it has a high column of it above the water, so it'll depress the water table. And if you want to remove this, our remediation methods have to draw on the mechanisms by which it gets there. So if you spill it, typically it'll take a few days, a few weeks, a few months to get to this resting point. And so long as nothing changes, it'll just sit there. And because interfacial forces are so strong, to be able to recover it, it's not very easy to do that just by sucking it out. If you put a drill hole in here and suck it out, you'd certainly be able to remove this free product, but you'd leave a residual amount in situ, and that residual amount will dissolve, as is shown by the stippling here, and get transported downstream. In this particular case, the water table has a gradient on it, dH dx. The head, remember what hydraulic head is? It's pressure over unit weight plus elevation plus v squared over 2g. Velocities are inconsequential. We throw those away, and we worried about what the change in hydraulic head is. It's basically given by the slope of the surface, and so this will allow us to define the velocity. You've seen Darcy's law, right, in your past. I'll write it in terms of hydraulic conductivity times the head gradient. So if we know what this head gradient is from this slope, we know that this is finite. If we know that this is a finite value, then this velocity is a value that we can calculate. And if we know what the velocity is, we know that this will be taken downstream to some kind of compliance point. And so that's the basic ideas that we'll use to talk about this. The stuff that's present within a single phase won't go anywhere. The stuff that is dissolving into the water-filled pores will dissolve into those pores by diffusing in this direction and then be carried downstream. So we'll talk about all the mechanisms that are involved in that. So it's two-phase flow for the first month, which is our first topic we deal with. Once it establishes it in place, the motion by which it's traveled is by diffusion, and then, which is topic number 3. In addition to diffusion, it gets carried downstream by advection, which is topic number 4. And topic number 5 is its mobility in the vadose zone. So we'll talk about all of those methods. If we talk about dry cleaning fluids, which still is a big deal, but now we're much more aware of it. These are denser than water, dense non-aqueous phase liquids. Dense being dense relative to water. So now if you spill them from the surface, then instead of stopping at the water table, they don't care. They just keep on going. So if you poured these into a swimming pool, they would sink to the bottom of the pool and have a puddle on the bottom. The equivalent of that for an aquifer would be a layer which doesn't allow it to cross. So this would be a layer where the hydraulic conductivity or the permeability is sufficiently low. 0, not infinity. And so this will act as the bottom of the swimming pool. And so these will just scoot on down. They'll pond at the base, so they might look like a puddle that's present at the base. It can't go anywhere. It could roll down this interface if it existed, probably won't. And it also will leave a smear as it goes down through here. The smear will be thinnest at the top and get progressively thicker because of saturation capillary pressure relationships, a topic we'll talk about in due course to understand how the proportion of the pore space is more completely filled as you get further deeper in the subsurface. And again, if you want to remediate this, just putting a straw in here would be okay in this zone. You'll be able to suck it out directly. But if you want to do it here, you'd probably suck out more water than the napple. And so that's not a viable way of doing that, and so you need another way of doing it. The natural mechanisms by which it will transport is that, in this case, this now is your groundwater table. This is your gradient of head. The velocity of the flow within that is going to be given by the hydraulic conductivity times this gradient. It's actually got a negative sign there because this gradient is negative, but the flow velocity is in this direction. Velocity is a vectoral quantity, not just a scalar. And so in this case, you have water passing through this smeared core of water and dry cleaning fluid, DNAPL. And so it will pick up some of this and it will carry it downstream as a plume. So the plume will progressively go further and further downstream, a little bit like what we'd expect here. You'd end up with a plume which would go like this, then it would go like this at increasing times. And so we want to be able to know how quickly does the concentration get to this point, because we want to know how we design to deal with it. We could, if we want, put a well in here and suck this out. And so we could stop it by going any further by doing pump and treat. But of course that wouldn't do anything to stop the source keeping on supplying very low concentrations of dissolved components, which are toxic to parts per million and parts per billion concentrations. And so if you never remove the source, you're left pumping and treating forever, which sometimes is a good way to do it because these do naturally attenuate themselves if you leave it long enough, probably not decades, but it might be cheaper to pump it and pay for the pumping, have it tied up in the courts and pay for lawyers than actually remediate the site, which can be a very big ticket item. And so these are the problems that we'll talk about. So we'll frame most of this class in talking about non-aqueous phase liquids, one, because it's the most important contaminant hydrology problem of our time, and secondly, it encompasses all of the other behaviors that we might want to look at. If we want to look at acid mine drainage, if we want to look at radionuclide transport from repositories, that's a slightly easier problem to deal with because we're dealing with single phase flow with radionuclides carried downstream. Here we're looking at two-phase flow. So it starts off being an innately more complicated problem. And so we'll need to, these are some old figures from a guy called Schwila, who used to do these aquarium experiments. Take an aquarium, fill it with sand, put some water in it, spill some dyed, denser than water fluid on the top, and look at how it gets smeared within the aquifer. See how it behaves in the vadose zone, spill it in the vadose zone, and then see what it does when it hits the water table. All these nice visualizations. And then look at the individual grains of the pores within the aquifer. So these would be pores, and these would be the individual grains, and it would be filled with water, but the colored fluids are actually the immiscible parts, which exist separately as separate fluids. And what they'll do is that they will form these ganglia, which if you think of these lighter, you can't see it very well here, these circular outlines are the beads, which are the bead pack, which is the porous medium. This is the stuff that's been spilled into the water, which is saturating this porous medium, and it's tended to take this tortuous path the way through here, because, I'll give away the punchline, because these are the pore throats which are largest and allow it to go through. The pore throats in this part of the aquifer are smaller. They aren't favorable to allow this through, and so this will just go through the small pore parts. And so we'll talk about understanding the mechanisms by which that occurs. And I'll stop there because we'll take that on next time. So that's the course conduct. Come to class if you wish, do it online if you prefer. 8 assignments, 1 midterm, and a remediation project to the deliverables. Again, it's Thursday at midnight to get the stuff done. It's a bit different from 303. It's not draconian. I guess I shouldn't say this. It's not Thursday night isn't a drop-dead deadline if you okay it with Matt first, I guess. You're probably better off just doing it on that schedule and getting into the swing of things. But it's a different class from 303. It doesn't have 100 students in it. It has apparently 15 delightful students about to graduate. And I guess the other thing is it's always a senior class, right? So seniors have senioritis. Yeah, I get it. You're ready to get out of here. But this is your discipline, right? For some of you, this will be a discipline. So this is a very pragmatic, can you believe it? A very pragmatic class that might put you off on the right trajectory for your first job. Some of the things that we touch on in this class might be the first things you do when you step into an office on the first day. Have any of you, in interns, have any of you worked for consulting companies or DCNR do some of these things?
I
Yeah.
did consulting for EPA and ODOT.
For groundwater?
We did like H&H reports, and some I went on like an infiltration test.
Yeah, fine.
That's the only experience
Yeah,
I
fine.
have with it.
Yeah, so some of you have seen some of this stuff. So this is typically, entry-level engineer stuff. Go out on a site and on a drill rig and work on it, log core, then take it back and design experiments to be able to say what's going on. So it's quite, it's a full package, I guess, what we have. So it's a fun class. I hope you enjoy it. So enjoy the cold. So any questions? Of course not.